Okay, so let us do the first problem of those TDS relations in order to calculate the change in entropy. So in here we have an insulated container divided in two, contains on one side 40 kilograms of water at 80 degrees Celsius and on the other 2 kilograms of water at 20 degrees Celsius. So like always we need a figure. So this is our rigid container, let's say it's connected by a valve. So this will be, we know right away this is a closed system. Then they also tell us that it's insulated, so what does that mean? Q equals 0. Contains water. So on one side there is 40 kilograms of water, and let's say this is M1 at 80 degrees Celsius, and on the other side you have 2 kilograms of water at a temperature of 20 degrees Celsius. So the water, so you open the valve, the water is mixed without any external action, so that means there is not any force applied to it, there is no mixer, there is nothing. Assuming a specific heat, so C equal to 4.2 kilojoules per kilogram Kelvin. We are asked to determine the final temperature of the mixed water and the entropy production, basically to determine if this is reversible or irreversible. But basically, do you think that if we have hot water on this side, cold water on this side, and then we mix the water, we're going to get warm water. Do you think we can get back hot water and cold water without any external action? Probably the answer is no, so that means that we need to find an entropy production that would be different than 0. So in order to find part A, basically, it's not that complicated. The only thing we need to do is using the first principle of thermodynamics, ignoring kinetic and potential energy, this will give us what? du. Okay, this is neglecting kinetic and potential energy. So we know that we don't have any heat because it's insulated, we don't have any external action, so basically what we have is that du is equal to 0. Now, in this case, what do we have? We have liquid water on this side and liquid water on that side. So let's say we can make the assumption of the ideal substance. Okay, so ideal substance assumption, which is what? That the change in internal energy is equal to mCv dt. Again, this is capital U, not lowercase u. So this is kilojoules and it's not kilojoules per kilogram. And we know, so we got this one. So if we combine this equation and this one, what do we have? So for the problem, what are we going to have? If I can zoom out just a little bit, we're going to have that M1, so let's say what would be the energy contained by the hot water would be mCv dt will be equal to what? So the final temperature of the mixed water minus the initial temperature, And then we need to look at what happened with the water on this side, and to CV, temperature of the mixed water, the final, minus the initial T2 will be equal to 0. Okay? So I need to go to the next page. So let me just rewrite that equation very quick. We have M1 CV T mix minus T1 plus M2 CV T mix water minus T2 equal to 0. So now we just need to do some basic algebra. So what we're going to have here is that M1 CVTM minus M1 CVT1 plus M2 CVTM minus M2 CVT2 equal to 0. So this is going to give us that T water, T mix times CV will be equal to what? M1 plus M2 will be equal to what? CV, move this one to the other side, M1 T1 plus M2 T2. So we can see right away that this will cancel, and we're going to get that the final temperature of the mixture is equal to M1 T1 plus M2 T2 divided by M1 plus M2. Alright, so we do the numerical application. You get that the temperature of the mixture is equal to what? So M1 is equal to 40. This is 80 plus M2 is 2 times 20 divided by 40 plus 2, and you get a temperature of 77.14 degrees Celsius. Okay, or in Kelvin, T mixture will be equal to 350.14 degrees Kelvin. Okay, so now we need to do part B. So part B, we need to find what is the change in entropy. Okay, so in order to do that, I don't like to just memorize equations. So let's say we use the equation, which is the first principle of thermodynamics, Q minus work equal to the change in internal energy. And we know that the S, the entropy, is equal to delta Q over T. Okay, so from these two equations, you can find that delta Q, which is the same thing as Q, will be equal to TdS. So we basically find the relation TdS minus the work will be equal to du. In this case, what is really the work? The work is PdV, but since the volume is constant, what would that be? Volume constant, dV will be 0, so really this is 0, so that means that this term is 0 over here. So basically at the end, the only thing we have is that T ds is equal to the change in internal energy. And using the ideal substance, we can write this as TdS equal to what? Same thing as we did before, m Cv dt. If we divide both sides by T, we get ds equal to m Cv dt over T. Okay? Or we get that the change in entropy, after integration, and I'm going to be quick over here, but this should be on the previous videos. The change in entropy should be equal to what? mCv log, let's say T2 over T1. But these are not the T1 and T2 over here, okay? This is a general expression. If you want, call this one T final and T initial, not to confuse anything. So T initial, T final. So for our problem, and I go to the next page, so for the present problem, what would be that equation? This equation will become what? The change of entropy will be equal to the change of entropy of the hot waters, will be m1 Cv log T mixture T1 plus m2 Cv log T mixture T2. So basically, what does that mean? Let's see if we can have some intuition over here. So this will be here, M1 is the hot water on this side. So what is the hot water going to do? Do you think as it mixes it's going to gain or lose energy? The hot water, as it gets cold, should lose energy. So we can think that maybe this value should be negative. Now, what happened of the water at 20 degrees as it mixes? The temperature is going to go up to what? 77.14 we had. So this term should be gaining. Okay, so this one should be losing entropy, this one should be gaining. But both of them cannot be equal to 0. We know that this needs to be always greater or equal to 0. Okay, so let's see what happens. So if we put the values over here, we're going to get what? M1 is 40, Cv we say is 4.2 log of 350 14 divided by 353, which basically is the 80 degrees in Kelvin, plus 2 times 4.2 log 350.14, and this should be what? 20 degrees Celsius in Kelvin is 293. And if you do the calculations, you're going to get that this one is negative 1.367 plus 1.496. So at the end, what do you have? You have that the total change of entropy of the system is equal to what? 0.129. So is that expected or not? Yes, because if you remember from the principle of increasing entropy of the universe, entropy always increases. If it is equal to 0, the system is reversible. But if it's higher than 0, the system is irreversible. Okay, and here what should be actually the units? This should be kilojoules per degree Kelvin. Okay, so this is a typical problem that you can encounter, and that's it. Thank you for your attention.